we present planning to explore via self-supervised world models. Reinforcement learning has shown some very impressive results in several domains. For instance, video games, board games, and even robotics tasks in simulation and in the real world. However, these agents are usually trained for a single specific task from scratch and require a large amount of task-specific interactions for each task. Since the training is done with task-specific rewards, the learned policy is difficult to generalize to new tasks. Self-supervised reinforcement learning has therefore been proposed as a way to learn skills that are not specific to a task but are generally useful and can later be adapted for downstream applications. In particular, recent works have pushed for self-supervised agents that learn behaviors via intrinsic motivation. However, most of these approaches use model-free policy learning, which is difficult to fine-tune and requires millions of samples to adapt to new tasks. Some other recent prior work incorporate model-based planning into exploration, but their results are shown from the state space and are difficult to scale to images. On the other hand, there are works that scale to images, but they either rely on random exploration data or have separate exploration and planning stages, which makes it difficult to model long-term dependencies. We propose a self-supervised model-based agent that is able to adapt to a new task in a zero-shot manner and works directly from images. Our agent, planned to explore, interacts with the environment without rewards in order to collect new data. It then uses the data to train a world model. Once the model is updated, the agent seeks to improve the model further by collecting novel data. After the model is trained in such self-supervised manner, we can use it to solve a specified task, such as standing, walking, or running in this case. A single self-supervised model can be used to solve all these tasks. Let us get into the details of how this is implemented. An input image is taken as the observation, and features are generated via an encoder. The features are then converted into the latent state of a world model. Given this latent state, a planner generates the actions that are then executed in the environment. A replay buffer collects the tuple of observation, action, and next observation, and this buffer is used to train the world model. No rewards are used at this point, as we don't assume that the task is known. The key idea of our method is to use long-term planning with the world model to explore the environment to collect novel data. This data is then used to train the model further to improve the exploration. The same model is then later used to plan for new tasks at test time. We now look further into the world model. The probabilistic latent state model is used to generate imagined rollouts of future latent states. It takes in a given feature of an observation and using the current latent state and action predicts the next states. In this imagined rollout of the world model, we generate intrinsic rewards for each step of the rollout. Our method will work with any self-supervised intrinsic reward formulation. Let us examine two specific choices of intrinsic rewards. First is the model error that says the agent should seek interaction that increases model error. On this toy example, where we are trying to fit a model to the blue function, we see that the model prediction, shown in gray, is good within the training data, shown in red, but has high error outside the training data. This is desirable since we want to incentivize the agent to visit the states that are exactly outside the training data. Now, let's look at model disagreement. Here, an ensemble of models learn to fit the same function. We see that the variance of the prediction is low within the training data, but grows outside it, as the members of the ensemble have very different predictions. So, are the model error and the disagreement the same? Let's see what happens on the training data in more detail. In the first case, the environment is deterministic. There's only one possible future observation, here shown as a blue dot. The model prediction, here in red, will be close to true data. Similarly, all the models in the ensemble will be close to the training data. So the model error and the disagreement are both low. However, what if your environment is noisy? Here, there are multiple possible future observations. In that case, the deterministic model will converge to the mean prediction, but will still have a very high model error. In contrast, if you have an ensemble, all the models in the ensemble will converge to the mean, and the disagreement will be low. We see that the model error metric conflates the uncertainty of the environment with the uncertainty due to missing knowledge, while the model disagreement only captures the uncertainty due to missing knowledge, that is, the epistemic uncertainty. The model error exploration strategy, therefore, will get stuck in noisy environments, while the model disagreement does not suffer from this issue. Furthermore, in the paper, we formally show that the ensemble disagreement approximates the information gained by our agent about the environment, confirming our intuitive analysis that it captures the epistemic uncertainty. Please refer to the paper for more details. Therefore, we use the latent disagreement of a bootstrap ensemble for our intrinsic rewards. The ensemble consists of one-step models, taking in the latent state and action and predicting the next image embeddings. The intrinsic reward is computed as the variance in the mean of the predictions of the next image embeddings. A practical consideration is that the ensemble is composed of lightweight one-step models that predict the encoding of the image. These intrinsic rewards are used as objective to plan for effective actions. To plan for long horizon behaviors, we use a learned value function. For fast inference, we amortize the planning procedure by training a parametric policy to produce actions. This policy can be learned via planning in the imagination of the world model without any new real-world interactions. This setup is the full training loop for Plan to Explore. Let us now see some self-supervised exploration behaviors learned by our agent. We evaluate our agent on 20 continuous control tasks using high-dimensional image observations as the only input, a few of which are shown here. Our agent is able to learn effective exploration policies on the tested continuous control tasks. However, these behaviors are still meaningless unless they can be useful for solving new tasks. So, how do we then go from exploration to being able to solve tasks? Recall that this setup is our training procedure for Plan to Explore. To solve a new task at test time, we use the train model and the same planning procedure to optimize task rewards. A new task policy is learned completely in the imagination of the world model, which allows to solve tasks in a zero-shot manner. A new reward predictor is trained for solving tasks at test time by relabeling the replay buffer with task rewards, without any additional interactions. To test our agent's ability to solve new tasks, we will experimentally see if our agent can solve a new task in a zero-shot manner, its performance when we provide a few supervised episodes, and finally, look into its multitask performance. We will now look at solving new tasks in a zero-shot fashion. We first show the behavior learned by the supervised oracle on these tasks, followed by a zero-shot agent. We see that even though our agent is not allowed to practice the new task, it is able to learn effective policies that solve the task in a zero-shot fashion. We show a comparison between our agent's zero-shot performance in green and the state-of-the-art task-specific agent in yellow. Our agent often achieves comparable performance to the oracle. On Hopper Hop, our agent in fact outperforms the state-of-the-art agent. Note that it doesn't see any reward nor state and only acts from raw images. This observation shows that the task-specific exploration might not be necessary to learn effective policies in these high-dimensional continuous control tasks. However, a small gap still remains between our zero-shot agent and the oracle. So how do we then bridge this gap? We can then look at what happens if we let the agent to practice the new task for just 20 supervised episodes. Here, our agent doesn't know the task before 1 million environment steps, so the rewards are low. However, once it is provided with the task, the performance of our agent climbs rapidly after just 20 supervised episodes. And on adding 100 supervised episodes, our agent is able to match the performance of the state-of-the-art agent. Comparing the behavior with the oracle, it is also able to adapt its behavior to the task very quickly, such as on the half cheetah task, where it is changing the behavior to a more standard one. We see that our agent is able to learn an effective model that can be used to solve a range of new tasks. Can a single model then be used to solve multiple tasks? Here, we show the results from a single model adapted to different tasks, such as running forward, running backward, flipping forward, and flipping backward. We also show a task-specific agent trained on running forward. While the task-specific agent fails on all the tasks it wasn't trained on, our task-agnostic agent is able to solve all the tasks very effectively. we see that our task agnostic agent is naturally suited for multitask reinforcement learning. To summarize, we achieve zero shot performance comparable to the supervised state of the art with only self supervised exploration. We match and even beat the supervised agent after adapting for just a few episodes. Our self supervised model generalizes to different tasks, while supervised agents only learn task specific models. And all of this with no supervision, no rewards, and no state information at training. Just planning to explore with self supervised world models. Please find the code and videos at this link. And thank you so much for your attention.